let us now look at the simulation of the sinusoidal PWM circuit. So this is the schematic of the sinusoidal PWM circuit. There are some things which I have written outside the page marker. So here is the power supply. I'm using power supply here, and this is the reference sine sources, modulating sources. And on this side I'm having a filter just to see whether you will be able to get back the fundamental modulating signal. And what is within the page border is the actual PWM circuit. So let us examine this. So let me expand. So this portion here, this is a triangle generator. It's a simple triangle generator which I have made using op amps. So you see here, this op amp, across the minus and the output I'm having a capacitor and then a resistor connected to the minus point coming from some signal. So this portion here, this portion which I'm indicating through the cursor is nothing but an integrator. So this is integrating. The output of the integrator, I am giving it to a comparator. It's a comparator with hysteresis. So I'm giving it to the comparator. So once the value of the integrator crosses this threshold, the trip points, you will see the output here going high or low. So if it is going high, then this integrator is integrating down. If this goes low, negative, then it is integrating up because it's inverting integrator. So the output here will be a triangle waveform going up and down, both positive and negative. So this is the triangle portion. So to the triangle, what do we do? So to the triangle we will add a small epsilon voltage to get the VC plus, and that is the upper triangle, and to this we will subtract a small voltage or the epsilon voltage to get the lower triangle. So how do we get the epsilon voltage? I am having this VCC to VEE potential division. This potential division is not of equal resistance. It is slightly offset. On the upper side I have 10.1K and it is 10K here. On a similar attenuator on the lower side I have 10.1K and it is 10K here. So when you take the center points here, this will be slightly negative and this will be slightly positive. So I am calling this one as ND lower, ND upper. So you use that one to add to the triangle. So to the triangle, you are subtracting it using a diff amp stage, and you will get the triangle upper. And then use the other one to subtract through a diff amp stage. I get the triangle lower. So this will be VC plus and this will be VC minus, carrier plus and carrier minus. Now use these two upper and lower carriers to obtain the PWM with dead band or the dead time. Okay, so now if you go to this portion, the comparator section, so you have the triangle upper connected to the minus, and to the plus you are having the sign reference. So the sign reference is this is again a hysteresis comparator, and the output of that will be the PWM. Now the sign reference given to the minus and triangle lower or VC minus given to the plus, this will give you the PWM bar, PWM A bar. If this is for the PWM A, this will represent PWM A bar with the dead time. Likewise, for the other arm, you use the reference B, compare with triangle with a triangle upper carrier, and you will get NB, and then use the reference to minus and the triangle lower to the plus, you will get NB bar. So these 4 signals you use to drive the switches: top, bottom of one arm, top, bottom of another arm. So if these are given to the full bridge switches, they will generate the desired PWM waveform at the center of the bridge. For the modulating signal reference, I am using sine, just giving an amplitude of 3 and 50 Hertz. And for the other arm, B arm, I am giving the same sine signal but minus 10 milliseconds, 180 degrees phase shifted. Now I am having this library. Within the library is the sub-circuit for the op-amp also. I have used a generic op-amp. Have a look at that one. And this here filter across the bridge arm A to B, I just put an RC filter to see if you will be able to extract the modulating signal, fundamental modulating signal. Of course, if you put a higher value of capacitance, you may get a much better, purer sine signal. So now let us simulate this circuit. And to simulate this, let us go to the terminal window. So I have opened the terminal window. So here I will run the simulation. So before I run the simulation, I would like to show to you the .cir file. Let us see the .cir file. So within the .cir file, so we have the trans statement. I'm going to see up to 40 milliseconds, which is 2 cycles. I'm going to use this PWM net and the usual, making the background color white, foreground color black, and running the simulation. What am I going to see? I am going to see NA and NA bar, and the voltage across the center arm V NA minus NB, that is across the center arm of the bridge, of the full bridge. Let us now go back to the terminal and run the simulation. I will use run sim PWM, so it will generate the netlist and then execute the simulation. So this is basically the PWM waveform. The red one here is NA, the blue one is NA bar. You are not able to see the blue one here because it is hidden behind the red one. Probably I will expand that and show. Yeah, you will be able to see the blue here. Yeah, so the NA bar, NA, NA bar, NA. They are mutually exclusive. The dead time being generated. The angle, rise time, fall time, is because of the print steps. So it is calculating at much higher resolution, but it is printing at a lower resolution of 10 microseconds. Okay, then coming back here, the yellow portion is the PWM signal, which you are seeing across the full bridge center arm, center portion. Just to cross check, I can see the voltage across the filter. Observe that I have given NA to here, NB to here, and I have put an RCR filter, and across the C I am observing there are 2 labels, NLA and NLB, and across NLA and NLB you will see the filtered portion of the PWM signal. So let us do that. You should see a sine wave. So let me plot voltage NL A, NLB. This case insensitive. So you will see that here, that the filtered portion. I have put a very low value of C, but you can as well put a large value of C and get a much smoother wave shape. Also note that there will be some harmonics due to the dead time that we are giving, and the dead time will introduce the harmonics and it will not be as pure a sine wave as we expect. The smaller the dead time, the better will be the sinusoidal extraction on filtering. So now I will leave this circuit for you to explore.